Linear programming. Linear programming is concerned with the maximization or minimization of a linear objective function in many variables subject to linear equality and inequality constraints. Linear programming is used to get the best decision among a wide range of alternatives. To illustrate the use of linear programming, we will take an example of X company where they are producing two types of shampoo, one for adult and the other one for kids. Each of these two types of shampoo should pass through two sections, backing, molding, and filling. The information provided in this example is that in the back molding section, we need 0.5 hours per unit to produce 1 unit of adult shampoo, and we need 0.2 hours per unit to produce one single kids shampoo, and the total labor capacity per day is 100 hours. For the filling section, we need 0.4 hours per unit to produce one adult shampoo, and we need 0.6 hours per unit to produce 1 unit of kids shampoo, and the total labor capacity per day is 150 hours. The following information is also given where the selling price per unit of adult shampoo is equal to 15 riyal, and the selling price per unit of kids shampoo is 12 riyal. The direct material cost per unit for adult shampoo is 3 riyal, and the direct material cost per unit of kids shampoo is 2 riyal. The direct labor cost per unit for adult shampoo is 4 riyal, and the direct labor cost per unit for kids shampoo is 5 riyal. Calculating contribution margin is straightforward, where we sum the cost of direct material and direct labor from the selling price. So, for adult shampoo, direct material cost per unit is 3 riyal and the direct labor cost per unit is 4 riyal with a total of 7. So 15 minus 7 is 8 riyal. So the contribution margin per unit of adult shampoo is 8 riyal. And the direct material cost per unit for kids shampoo is 2 riyal, and the direct labor cost per unit for kids shampoo is 5 riyal, so the total is 7. So the contribution margin per unit is 12 riyal minus 7, equal to 5 riyal. So the contribution margin per unit for kids shampoo is 5 riyal. In linear programming, we are looking at maximization of profit. And the question here, how much we should produce from each type of shampoo to get the maximum profit under the given constraint. Please note that here we can produce all units from only adult shampoo, and we can produce all of them from kids shampoo, and we can produce any sort of mix. Clearly, we will have so many alternatives to look at, making it impossible to solve for each possibility. We will assign letter X for adult shampoo and the letter Y for kids shampoo to be used in solving the equations. And the objective function, and we call it Z, will equal to Z equal to 8x plus 5y, where 8 is the contribution margin for adult shampoo and X is the number of units need to be produced from adult shampoo, and 5 is the contribution margin of kids shampoo, and Y is the number of units produced or need to be produced from kids shampoo. We need to look at constraints, and in each section the constraint is the labor capacity per day. So for back molding section, we can write this equation where 0.5x plus 0.2y is equal or less than 100. 0.5 is the number of hours needed in the back molding section to produce one single unit of adult shampoo. And X, as we mentioned earlier, is the adult shampoo number. 0.2 is the number of hours needed to produce one single unit of kids shampoo in back molding section. And Y is the number of kids shampoo aimed to be produced. 100 is the maximum labor capacity per day. For the other constraint in the filling section, we can write this equation: 0.4x plus 0.6y is equal or less than 150, where 0.4 is the number of hours needed to produce one single unit of adult shampoo in the filling section, and x is the number of adult shampoo, and 0.6 is the number of hours needed to produce one single unit of kids shampoo in the filling section, and y is the kids shampoo. And 150 is the number of labor capacity hours per day. Now we need to solve the two equations together, and we can replace the sign of less than or equal by equal, since this is the maximum production. We can start by solving any one of the two equations, and let's say that we started with the second equation of 0.4x plus 0.6y equal to 150. So 0.6y will equal to 150 minus 0.4x, and dividing by 0.6 for the both side of the equation, so y will equal to 250 minus 0.67x. Now we need to replace the value of y in the other equation. So 0.5x plus 0.2y equal to 100, and that will equal to 0.5x plus 0.2 between two brackets, the value of y, 250 minus 0.67x, and that's equal to 100. And that will equal to 0.5x plus 50 minus 0.13x equal to 100. So 0.5x minus 0.13x equal to 100 minus 50 by rearranging the formula. And then 0.367x equal to 50. So x will equal to 50 over 0.367, and that's equal to 136. Now we need to replace the value of x in the equation of y to get the result of y. So y equal to 250 minus 0.67x. So y equal to 250 minus, between two brackets, 0.67 multiplied by 136, and that will result in y equal to 158. As per our result, x equal to 136 and y equal to 158. So to achieve the maximum profit, we need to produce 136 units of adult shampoo and 158 units of kids shampoo on daily basis. To test our results, we will call our objective function where z equal to 8x plus 5y. Let's assume first we produce only kids shampoo, so adult shampoo will be 0. So z equal to 8 multiplied by 0 plus 5 multiplied by 250. The 250 here is the maximum production of kids shampoo according to the constraints available. So the end result will be 1250 Saudi Riyal per day. In case that we produce all of the quantity from adult shampoo, then we will replace Y with 0, which is kids shampoo. So 5 multiplied by 0 equal to 0, and 8 multiplied by 200, and 200 here is the maximum production of adult shampoo under the constraints explained earlier. So the end result will equal to 1600 Saudi Riyal per day. Let's right now test the situation or the profit from producing both of them with the numbers that we got them earlier. So Z equal to 8 multiplied by X, the adult shampoo 136, plus 5 multiplied by the number of kids shampoo 158, and all of that equal to 1878. And this number is more than the value or profit that could be achieved if we produce only adult shampoo or only kids shampoo. We can also solve this problem using a graph. We can draw adult shampoo in the y-axis and the kids shampoo in the x-axis with the appropriate units used. We will call back also our constraint equations where 0.5x plus 0.2y equal to 100 is the backing molding equation constraint, and the 0.4x plus 0.6y equal to 150 is the equation for the constraint related to filling section. Let's look first for the first equation related to back molding section, and let's assume the two opposite scenarios where we produce all of our units from adult shampoo or we produce all of our units from kids shampoo. So if we produce all of our units from adult shampoo, then we replace y with 0, so 0.5x plus 0.2 multiplied by 0 equal to 100. Solving this equation will result in x equal to 200, or the maximum production of adult shampoo will be 200. If we assume that we are producing all of the units in the back molding section with kids shampoo only, so we will replace the X adult shampoo with 0, so 0.5 multiplied by 0 plus 0.2 multiplied by y equal to 100. Solving this equation will result in y equal to 500. So the maximum production from the kids shampoo related to back molding section is 500. With the first constraint of back molding section, the maximum production of adult shampoo is 200 and the maximum production of kids shampoo is 500. So we draw a line between 200 of the adult shampoo to 500 of the kids shampoo. Under the second constraint, we will call back our equation of 0.4x plus 0.6y equal to 150. So if we assume that we are producing only adult shampoo, so y will be 0, so 0.4x plus 0.6 multiplied by 0 equal to 150. Solving this equation will result that x equal to 375. And if we assume that we are producing only kids shampoo, then we will replace x by 0, so 0.4 multiplied by 0 plus 0.6 multiplied by y equal to 150. Solving this equation for y will result in y equal to 250. So under the filling department constraint, the maximum production of adult shampoo is 375 and the maximum production of kids shampoo is 250. So we draw a line between the adult shampoo 375 to kids shampoo of 250. We look now at the crossing point between the two lines, and we draw an arrow down to the kids shampoo, and this will result the maximum production of kids shampoo that will provide the maximum profit. And if we draw another line between the cross of the lines to the adult shampoo, we will find the maximum production of adult shampoo that will provide the maximum profitability. Please note that these numbers should exactly match what we calculated earlier with equations.